Oh. All right, my boy. Today, we're hoping to conclude chapter 2 that we started in lecture 3. Um, Different ambiance, and then my pop setup. This shit kind of clean. Got his own like camera. Got a necklace. All right. Anyway, let's get into it. So let's answer the question: what is an algorithm? Machine learning uses various algorithms to iteratively learn from data. Um, Algorithm is typically a self-contained set of rules that is used to solve a problem in data processing using math or some sort of automated reasoning. Machine learning algorithms use computational methods to learn information directly from data without relying on a predetermined equation or model. As we covered in the last lecture, it actually learns the equation that it's attempting to model. So we have a classification algorithm, and then whether we have two class or that binary classification that we would typically represent with an activation function known as the sigmoid function, or whether we're going to have multi-class classification where it spits out probability indexes over the course of multiple categories. You know, that's all I think. 2024 Biden says to pass the torch to a new generation. Well, that's awesome. Good for Biden. What a noble young man. Example, how to classify the data points. How? No, take a second. How would you classify this data set into two categories, red and blue? How can we draw a best fit line that encapsulates that accurately represents two sides? You'll notice that there's some intersection between red and blue, but how can we deal with those outliers? How can we deal with the blending in the middle? Um, an accurate guess. So if I were to just draw a linear line through this from one corner to another, uh, I miss on a good chunk of these red here. I may miss that chunk of red. And consequently, this chunk of blue. But what we can do, again, based off the complexity of the model that we want to compute, based off the power or the uh, the degree of the polynomial of the equation that we're going to use to represent the line, we could have theoretically a line that overfits, that learns the training data, this data, 100%. You could have a polynomial that goes perfectly around each one of the blue points and intersects over all the red and encapsulates it perfectly. That's a problem in machine learning known as overfitting, where we have a line that literally is 100% accurate. Um, it didn't learn about like it didn't learn how to predict. It learned the training data very well. And the evaluation data, it may score very poorly on the evaluation data, but we want a line that best models this. So we can do this using some sort of curve, maybe like one or two curves in there to better represent it, things of that nature. How can we accurately dissect this into two categories? There, there are many ways that you can do that. These are just a couple of the solutions using different algorithms to solve the same set. You can see here in the nearest neighbors, this is a sort of clustering algorithm where we predict centroids or the centers of groups. And if you lie closer to one center than another, then you're assigned to the given group that you're closest to. So here we can see the centroids, one in the middle, and then one in this blue region down here. We see light red for indicative of somewhat middle ground, but also some light blue. Um, but these are all various algorithms we can use: the Gaussian process, the decision tree, random forest, neural net, naive Bayes. Uh, yeah, I think this is a great example of just how many variations we can have when tackling a problem, and how would which one's the best? Well, it's difficult to say. There's a wide range of algorithms, and this goes over some of them. You have ordinary or ordinal regression, just like typical linear regression. You have Bayesian regression, which predicts event counts. Of course, that gets into the realm of probability and Bayesian distributions. Um, you have the fast forest linear regression, but the Bayesian, I actually don't know how to pronounce it. If it's Bayes theory, then it's Bayesian linear regression, neural network regression, decision forest. Of course, you have the clustering on, if you remember from like one of the first lectures, that this is actually a form of unsupervised learning where labels are not needed and it merely learns intrinsic patterns in the data. This is an unsupervised type of learning, clustering. Okay. Then you have anomaly detection, two class, two class classification. This is again your binary, and then you have multi-class classifications. Again, as we went through supervised, unsupervised, semi-supervised, and reinforcement. And some of these models, of course, are clustering is typically used for unsupervised learning. These certain algorithms have certain wheelhouses. Then we move on from the model itself to evaluating said model. We go from training to evaluating how well the model did on training. So what's a good model? Are we accurate? Okay. Are we interpretable? How easy is it to explain the predictions that we made? All right. How fast does it take the model to build itself? Are there, what's the training time looking like? Does this take you 8 months or did it take you 8 minutes? And then how scalable? How much longer do I have to wait if we build and predict them, if we were to retrain the model using more data? Okay. Does this model make predictions in real situations? We can be very happy during the training, and then it could do very bad while actually applying the model. The model make if the model begins to make perfect fitting during the training phase, there is um zero zero difference between the expected value and the output value of the model. This is an issue known as overfitting. And the cost or loss function, we attempt to minimize that, as I stated in the last lecture. We attempt to minimize the cost function. And any the value generated in that cost function is how you say, um, it's used to descend the gradient. Okay. This is about to get crazy, boys and girls. So buckle up. This is about to get wild. You're gonna have to put your thinking caps on for this one. All right. Let me see. Can I see over here? Excellent. Cool. So let's say that clear all drawings. Okay, cool. Let's say we have a graph. Actually, I'll do this. Let's say we have a graph here. We have a local minimum, big jump, and then a global minimum. This is the lowest point on the graph. Okay. We seek this, and this is a representation of the cost, right? We seek to minimize the cost. We want it at its lowest possible point. Oftentimes, and this is what is known as descending the gradient, to seek out and find a way to reach the global minimum. Okay. So assuming we're starting at 0 over here, and then over here at some arbitrary value, we seek to descend and minimize the cost, where the cost is given by C here. We seek to minimize and hit this point here. The problem is, as we start, we may shrink and shrink and shrink, but then we may grow. We've hit a local minimum. It's possible. It's possible to be stuck in this region, okay, and not ascend the hill of errors and higher cost to ultimately reach the lower minimum, okay, the true global minimum of the graph. Um, If I were to get into an instance where the the training data is 100% accurate and there's no error, there's no cost of the model, guess what? The cost is used to descend the gradient. How much do I descend in this direction? Okay. If I'm 100% accurate, guess what the cost is? It's zero. We can't descend the gradient. We can't move anymore. So, that being said, we could have an issue where we get stuck in a local minimum and then um the model doesn't learn anymore. It fails to improve and generalize more and more. Oh, I have to exit out of this. Oh, I have to click on this. So about model fitting, we have underfitting where it doesn't accurately represent. We see some data points that are somewhat far. They have a high Euclidean distance, and which is literally just if I were to draw a straight line from A to B, that's the Euclidean distance. Don't let that scare you, but I like to use big words because they sound smart. You have good fitting, which accurately models the data to a high degree. And you have overfitting, where it learns the known data to such a degree that it fails to consider new data. It wants to stick to the exact path that it knows. You got to remember, models are not, none of them are right, but some of them are useful. This model has the opposite happening. This model is correct. It's no longer a model, it's represented, it's literally the real data. But we don't want that. We want something that predicts trends. We want something that generalizes. We want something that doesn't just regurgitate the data that we fed it. We want inferencing to occur. Overfitting a model with no training error and high test error, it leads to it can't be applied to new data, although it performs extremely well during training. Here we have underfitting, good fitting, where we somewhat accurately represent, and then overfitting. Like I mentioned on the other example, we can have a high degree polynomial that twists and turns through each data point and accurately represents it. The goal is to find a trend, not to be right. So here we have underfitting versus overfitting. When a model fails to capture important distinctions and patterns in the data, it performs poorly even in training data. That's called underfitting. Underfitting is often a result of an excessively simple model, all right? An excessively simple model would be a linear regression model, so not a high enough degree polynomial. It doesn't have any turns, twists, or any capability to do so to accurately model the data. Versus here we have x squared, at least x squared because it has a single point of inflection, but we at least have x squared here, then with some manipulation done to the graph. So maybe, some slight tilting, some slight reflection, some translation occurs, of course, that occurs there. But yeah, this is how we do, baby. Um, then we get into the issue of overfitting. Overfitting is when a model performs perfectly on training data, but fails to predict well on new data. In other words, it has low training error, but high test error. Both overfitting and underfitting lead to poor predictions on new data sets. This example demonstrates the problems of underfitting and overfitting and how we can use linear regression with polynomial features to approximate nonlinear functions. Most data in the real world will be nonlinear. Because excuse me, if data is linear, is often highly recognizable, and more often than not, we don't need machine learning to solve a linear problem. It would often be too simple. A polynomial of the fourth degree approximates the true function almost perfectly. However, for higher degrees, the model will overfit the training data. It learns the noise of the training data. Okay. A fourth degree polynomial, as I said, the higher the degree the polynomial, the greater the potential points of inflection. If a model is too complex, it has too much stickiness to the data. Hence the need to appropriately to model it in the simplest way possible. Model validation checks how well a model generalizes to new data. Reserve or split a portion of the total data to validate the model's performance. As I mentioned, we split into training sets, and test sets. We will take a portion. So let's see how many rows. Oh, sorry. 40, no, sorry, 60 to 80% is for training, 20 to 40% is for testing. Those numbers are usually up for debate, but that's just the industry practice. We want to evaluate the model to estimate the quality of its pattern of generalization. The only way to know how well the model will generalize is to test it on new cases. It's common practice when performing supervised learning to hold part of the available data set as a test set. There are different validation strategies that we can use. We have holdout validation, k-fold cross-validation, and leave one out cross-validation. So here's our holdout validation. Split the data into two parts, training and test set. The holdout validation is a very simple type of validation. Okay, here we have the ratios that I was mentioning. We have the data set as a whole, and then we just split it. This data is never seen during training. This data is held, it's isolated, it's held off to the side for validation and testing purposes after the training data has been iterated through multiple times. The machine learning system evaluates predictive performance by comparing predictions on the evaluation of the data set with known true values, i.e. the ground truth or the labels of the samples, using a variety of metrics. However, its evaluation can have high variance. The evaluation may depend heavily on which data points end up in the training set and which end up in the test set, and thus evaluation may be significantly different depending on how the division is made. If it is possible, let's say I'm doing weapon detection, and it just so happens it's a random chance, but I split the data set, and let's say in the training data, I have all black pistols. Okay. And it just so happened this way. But in the test data, I have pink rifles. It may fail to accurately identify a firearm because of the split that we made in the data. It just so happened that the the um the data instances didn't have enough representation in the training. It is possible to have, using this method, that we don't train over all the appropriate cases, just because of how we choose to split it. A better approach is to split the data into training and then use cross-validation and a test set, okay? Use your cross-validation set to select the model and evaluate it on the test data. This approach is, of course, recommended by Andrew and G. We have the full data set, and then we randomly hold out part of the data. Randomly is key for cross-validation and testing, okay? For relatively small data set, usually like maybe, oh, there you go, 1,000 to 10,000 samples. For super large data where there's millions, we use as much of that data as we can for training. And then a smaller portion for the testing data. So cross-validation and k-fold cross-validation. K means clustering. K is a variable. K is any number that we choose to put in, right? So let's say we have a data set. If I do k-fold cross-validation, K is indicative of any number of cross-validations, and I choose that number as the developer. I can choose to do 5 folds. I can just do 2 folds. I can split how do I want to split the data into large sections or into groups and test it that way? The data is divided into K number of subsets, and the holdout validation is repeated k times. Each time, one of the k subsets is used as the test set and the other k minus one subsets. So the remaining difference, the remaining number of things that aren't being used for testing are put together to form a training set. Then the average error across all k trials is computed. And that will give you your validation results. How accurate was your model? So here we can see we use all this data for training and then the top 20% for testing. Then we use the middle 20% for testing on fold 2 and 3. And then the fourth one, and then the fifth. And then we sum up all the errors. We do a summation of the errors and then um, take the average of these errors. The advantage of this method is that it matters less how the data gets divided. You won't have the issue about pink rifles and black handguns, and like one type of firearm being represented more or less in the data. Because you have to keep in mind, at the end of the day, these learning models operate off of data. If I only give them one example of something, if I gave you one example of how something works, it's not adequate. It's one instance of something is not enough to establish a pattern. Therefore, we need as many data instances as possible in order to establish that pattern in the data. So computers work the same way. We have to have values. We have to have enough values in order to establish a pattern. Okay. And this avoids that issue by iterating over everything gets used for testing and training. The variance of the resulting estimate is reduced as k is increased. So the more folds that you do, the variance is decreased. The disadvantage of this method is the training algorithm has to be rerun from scratch k times using a different training, of course, a different training and testing set each time. This makes computation a lot more arduous. It is much more difficult here. And it is directly correlated to the number of operations that you have to do. So it's rough. Which validation strategy should we use? On a large data set, use holdout validation. You have enough data. It's unlikely that there you won't capture instances like of anomalies in the training and validation set. You don't have to worry about not getting any pink rifles or black guns in the training data because it's so large, it's almost impossible um, not to capture uh, all the subsets in the data. In small data, we should use cross-validation because there is an issue where if we only have 10 images, two of them are pink rifles and 8 of them are black handguns, there's a possibility that if I'm selecting 2 or 3 images for testing, that pink rifles are never considered in the training data. There's that possibility. Cross-validation is useful when the data set is small, where cases where not much training data can be held out to reliably estimate test performance. Tenfold cross-validation is common, but smaller k values are often used when learning takes a lot of time. Again, that computational efficiency is key. There are times that machine learning models take days, hours, or weeks to run. And if you have to wait weeks, at a minimum of 10 weeks for results, in some areas, that's just not appropriate. Evaluate the model's performance. How is my model doing? We evaluate the model on test data, and then we determine if it's doing good or not. It measures the quality of machine learning and determines how well our machine learning model will generalize to predict on new target data once it's deployed into the real world. Some of the things that we learn here are some of the metrics used to evaluate model performance are accuracy, okay, precision, recall, and F-score. These are some big ones. And then of course you have your various cost functions. Cost functions are also an appropriate way to measure the difference between the expected and generated outputs. So you have mean absolute error, mean squared error, root mean squared error, and things of that nature. Um, and check me on this. Matter of fact, I'll ask Google, but first I'll test myself. Accuracy, if something's accurate, that means you're close to the desired goal, but accuracy does not imply precision. Precision is like if I'm out shooting and I get close to the target, the bullseye, I'm accurate. But if I'm way off the target and I hit a tree, but all three shots hit the tree, then I'm precise. I'm not accurate, but I'm precise. Those things are they're not mutually exclusive. They do not have to exist simultaneously. So let me look up accuracy and I'll share my okay. Let me see. So precision and accuracy are two ways scientists think about error. Accuracy refers to how close a measurement is to the true or accepted value, and the precision refers to how close measurements are um, to one another. So I'll share my screen real quick. Should be able to see my screen. These are indicative of we have um, we have low precision and low accuracy. We have high precision but low accuracy. We have high accuracy but low precision. And then we have both high accuracy and high precision. I need to meet whoever's shooting that because that's fucking impressive. Anyway, again, this is just the things we went over on the last slide: accuracy, precision, recall, and F-score. Accuracy is the number of correct outputs over the total number of predictions made or the cases evaluated. Um, and here we can get into there's a fun I don't even know. I don't think you'd call it a paradox, but there's an issue that occurs among rare items. Okay. Um, if I have a false positive rate where I misidentify people with cancer at a rate of 5%, but cancer is only prevalent in 3% of the population, it's more often than not that you'll, instead of actually detecting cancer, it's more often than not that you'll detect a false positive. Um, it's an interesting concept. I'd have to look it up and kind of understand a little bit more to fully explain it, but it's something worth considering that if your margin of error is greater than the anomaly or the thing that you're predicting is present, it's more often than not you're going to get false positives. Accuracy is not a good metric for skewed data sets. A predictive model may have high accuracy but be useless. Um, Suppose the positive class is only a tiny portion of the observed data. Only 1% of patients have true cancer, while 99% of patients don't have cancer. This is a typical case about data skew. For imbalanced classes where we have more representation in one class uh, than another, and when I say class, I mean like a category. The class is a category. It's the class, literally classification. Which group are you going into? Um, for such imbalanced classes or categories, suppose you build two models. Model A would achieve 99% accuracy by always predicting not cancer. Model B has 75% accuracy. It correctly predicts some cancer cases, but also makes some misclassifications, right? If the model just always says no cancer, it's going to be right 99% of the time because only 1% of patients have it. Not that big a deal. Of course, it's going to be right 99% of the time. It just says no all the fucking time. Therefore, the model doesn't really, it accurately does it, but it's not detecting what we want it to. Model B has accuracy of 75%. It correctly predicts some cancer, but also has false positives. Is Model A better than Model B? Absolutely not. Incoming data as negative classes, i.e. no cancer, can achieve 99% by consistently always saying no, but can identify cancer when it is there. So therefore, the model is completely useless. Using accuracy is only good for symmetric data sets where the class distribution, where the categories are 50-50, and the cost of false positives and false negatives are roughly the same. Here's we'll get into a confusion matrix. Shows more details about it's merely a visual representation of true positives, true negatives, false positives, false negatives. Okay. Binary classification. Here we have the negative class and the positive class. Some positive classes are classified as negative values. Some negative classes are wrongly classified as positive. So here we go. This is the confusion matrix that I mentioned. Positive, 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 negative, 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 and negative, positive. So a true positive is, of course, when we say we predict somebody has cancer and they do have cancer. A true negative is when we say this person does not have cancer and it is correct that they do not have cancer. Then you have a false positive, of course, where we say somebody has cancer, but they do not. And then we have a false negative where we say somebody does not have cancer, but they do. But we've reported it as no. It's a false negative. Yeah, yeah. And anytime it's preceded by the false, of course, this is an error. Metrics for evaluating regression models. These metrics returned for regression models are generally designed to estimate the amount of error. A model is considered to fit the data well if the difference between observed and predicted values is small. However, looking at the pattern of residuals, the difference between any one predicted point and its corresponding actual value can tell you the potential of bias in a model. So here we have a linear regression error. Suppose you want to create a simple model for predicting house prices based on room size. A linear regression model can be built predicting the house price, right? And here's the equation of the line and the coefficient of determination, 93%, which is fucking great. Here we can see the prediction error. Okay, you can compare the observed results with predicted values. Such error can be used to evaluate the model's performance. So here we measure the Euclidean distance from a data point to the model's value. So the y hat, okay, the y hat is the predicted value. It falls on the line. This is the trend line. This is the generalization. This is the output of the model. And then the yi, this data instance, that's the data. That's the known value that we have. And we can generate by measuring the distance between the predicted price and the actual price, we can come up with the difference. And that difference can be used to measure how wrong the model is, of course, the error. So we have a $50,000 error. Now, if an AI, let's say you list your price on Zillow and they give you an estimate, if you sold your house for $57,000 less than you could have gotten, are you going to be pissed? Absolutely. Common metrics for measuring the regression of errors. A smaller value is a better value. Low errors mean the model is generalizing well. So for a regression model, oh, I just kind of want to see what slide I'm on. Okay, 5 more slides. Metric for a regression model is the mean average error or mean absolute error. The mean absolute error measures how close predictions are to the actual outcomes. Of course, you have the predicted value, right? Y hat. And then you have y, just the regular y, which is your labeled data, the actual instance. You measure the difference, you take the summation, and then find the average. And this is put in absolute value bars. The reason for this is, the reason why we take the absolute value is because let's say I have so these two data points. We have this data point, okay? And then we have this data point. One is, let's say they're both, those lines have the same what's the word I'm looking for? Don't tell me. They have the same amplitude. They're the same distance from the outcome, from the expected real world result. If I don't take the absolute value of the error, guess what happens? If I'm $60,000 short on one prediction, but then $60,000 over on another, when I do the summation of negative 60,000 and 60,000, they cancel out. And so that would result in a model with no error, which is incorrect, obviously. It was $60,000 short and $60,000 over. There's something wrong. We have to take the absolute value and measure the amplitude. How the absolute value, the distance. We don't care what direction it's in. We just care that the distance is wrong. Okay. That's why we use the absolute value here. Mean squared error, okay, it acts similar to the mean average absolute error in the sense that whenever you square a value, it can't be negative. Okay, so when you square something, it eliminates the possibility of that those two terms canceling out. You still get the magnitude, but the purpose of mean squared error is by squaring the difference. Guess what you do? You penalize results that are further away. So if I have a really small, let's say I was $1 off on house price. Well, one squared is one. It's not that big a deal. But let's say this is $4 off on a house price. Well, then the error becomes the difference between the expected value and the real value is, expected value and the output value is 4. When we square it, it becomes a difference of 16, and that results in a larger error. Again, I went over this formula. This is merely a summation sign of n number of samples, okay, and with I starting at 1. And then, of course, we have the y hat, which is the output. We have the yi, which is just the expected value. We square that, we do a summation of all those values, and then we divide it by the number of samples that we considered. All it is, we take an average of the difference squared, mean squared error. Because of the square, the negative values don't cancel and they become positive. And this also amplifies the impact of errors. Because of the square, large errors have relatively greater influence on mean squared error than the smaller errors do. And again, the better the square, the better. Then we have root mean squared error. This is the exact same thing, but now slapped in a square root. This is the most popular evaluation metric used in regression problems. It has the same unit with y. Root mean squared error may be the most common metric, but it has some problems. It is highly affected by outlier values. It more aggressively punishes big errors than small ones. This means root mean squared error should be more useful when large errors are particularly undesirable. And then you have mean absolute percentage error. It measures the size of the error in terms of a percentage. This is best when there are no extremes in the data, including zeros. In spite of popularity in measuring the forecast error, the mean absolute percent error has major drawbacks in practical application, and it should be used cautiously. It can give a distorted picture of the error. The error on a non-zero item can be infinitely high, causing a distortion of the overall error rate. So of course, this could be a problem. So in summary, identifying business goals and defining data mining goals with respect to your situation is key. Machine learning involves many topics and domain fields that we can go converse with experts in. You can find a flavor or problem or industry that not only aligns with your coding, AI, and computer science goals, but also one that that you have a vested interest in, such as the biomedical domain, or excuse me, or if you're into chemical engineering, you could go do AI for some automation practices at chemical plants and oil refineries. You could do medical diagnostic imaging and all sorts of things. You can find ways to almost be a jack of all trades with this. And then you can construct machine learning methods that depend on specific problems in industries. And I look forward to any questions you may have. Thank you. And we'll get into chapter 3 next time.